Quick recap of the first derivative. F prime of x equals the limit of f of x plus h minus f of x over h as h approaches 0. It gives the slope of the tangent line at any point, the instantaneous rate of change, and in physics, the velocity when y represents displacement. On the graph, watch the dot trace the position curve s of t equals 0.4 t squared. At time t equals 2, the tangent line has slope 1.6, that's the velocity at that instant. The second derivative. F double prime of x equals d squared y over dx squared. It's the derivative of the derivative, the rate of change of the slope itself. In physics, if displacement is y, the first derivative is velocity, and the second derivative is acceleration. Geometrically, it tells us the concavity of the curve. When f double prime is positive, the curve is concave up, it curves like a cup that holds water. The slope is increasing. When f double prime is negative, the curve is concave down, it curves like a cap. The slope is decreasing. Example. Find f prime and f double prime for f of x equals x to the 4 minus 6x squared plus 8x plus 5. First derivative, apply power rule to each term. F prime of x equals 4x cubed minus 12x plus 8. Second derivative, differentiate again. F double prime of x equals 12x squared minus 12. Setting f double prime equal to 0, 12x squared equals 12, so x equals plus or minus 1. These are inflection points where the concavity changes. On the graph, notice how the curve switches from concave up to concave down at these points. Application 1, rate of change. The derivative dy by dx gives the instantaneous rate at which y changes with respect to x. In physics, velocity is the rate of change of position, acceleration is the rate of change of velocity. In biology, growth rate is the rate of change of population. Visual example, consider a circle whose radius is expanding. The area A equals pi r squared. How fast does the area change as the radius increases? Da by dr equals to pi r. So as the radius grows, the area increases faster and faster, the rate of change itself grows. Example. A spherical balloon's radius increases at 2 centimeters per second. Find the rate of volume increase when radius is 5 centimeters. Volume of sphere, V equals 4/3 pi r cubed. By chain rule, dv by dt equals dv by dr times dr by dt. dv by dr equals 4 pi r squared. And dr by dt is given as 2. Substituting r equals 5, dv by dt equals 4 pi times 25 times 2 equals 200 pi, approximately 628 cubic centimeters per second. Application 2, increasing and decreasing functions. If f prime of x is positive on an interval, the function is increasing, the curve goes uphill. Shown in green. If f prime of x is negative, the function is decreasing, going downhill. Shown in red. Where f prime equals 0, we have critical points, these are potential maxima or minima. On the graph, the function increases where f prime is positive, reaches a local maximum where f prime becomes 0, decreases where f prime is negative, and reaches a local minimum before increasing again. Application 3, tangent and normal lines. The equation of the tangent at point x1, y1 is y minus y1 equals f prime of x1 times x minus x1. The normal is perpendicular to the tangent. Its slope is negative 1 over f prime of x1. Their slopes multiply to give negative 1. On the graph, the blue line is the tangent, it touches the curve at exactly one point and has the same slope as the curve there. The red line is the normal, it's perpendicular to the tangent. Notice the right angle between them. Example. Find the tangent and normal to y equals x squared at the point 1, 1. First, find the slope, y prime equals 2x. At x equals 1, slope equals 2. Tangent equation, y minus 1 equals 2 times x minus 1. Simplifying, y equals 2x minus 1. Normal slope is negative 1 over 2. Normal equation, y minus 1 equals negative 1/2 times x minus 1. Simplifying, y equals negative x over 2 plus 3 over 2. Application 4, maxima and minima, the most important application of derivatives. A local maximum is a point where the function value is greater than or equal to all nearby values. A local minimum is where it's less than or equal to nearby values. At both maxima and minima, the first derivative equals 0, these are critical points. On the graph, the tangent line is horizontal at both the local maximum and local minimum, the slope is 0. But f prime equals 0 alone is not enough. We need tests to determine if it's a maximum, minimum, or neither. First derivative test. Step 1, find where f prime equals 0 to get critical points. Step 2, check the sign change of f prime around each critical point. If f prime changes from positive to negative, the slope goes from uphill to downhill, it's a local maximum. Like a hilltop. If f prime changes from negative to positive, downhill to uphill, it's a local minimum. Like a valley. If the sign does not change, like positive to 0 to positive again, it's neither max nor min, just an inflection point. Second derivative test, often faster than the first. At a critical point C where f prime is 0, if f double prime of C is negative, the curve is concave down like a hilltop, it's a local maximum. If f double prime of C is positive, the curve is concave up like a valley, it's a local minimum. If f double prime equals 0, the test is inconclusive, you must fall back to the first derivative test. The advantage, you only need to evaluate f double prime at one point instead of checking sign changes on intervals. Example. Find the local maxima and minima of f of x equals x cubed minus 3x plus 2. Step 1, f prime of x equals 3x squared minus 3, which factors as 3 times x minus 1 times x plus 1. Setting f prime equal to 0, x equals negative 1 or x equals 1. Step 2, use second derivative test. F double prime of x equals 6x. At x equals negative 1, f double prime equals negative 6, which is negative, so x equals negative 1 is a local maximum. At x equals 1, f double prime equals 6, which is positive, so x equals 1 is a local minimum. The maximum value is f of negative 1 equals 4, and the minimum value is f of 1 equals 0. Two fundamental theorems. Rolle's theorem, if f is continuous on the closed interval a, b, differentiable on the open interval a, b, and f of a equals f of b, then there exists some c between a and b where f prime of c equals 0, a horizontal tangent exists. The mean value theorem, also called Lagrange's theorem, is more general, f prime of c equals f of b minus f of a divided by b minus a. This means somewhere between a and b, the tangent line is parallel to the secant line joining the endpoints. On the graph, the orange secant connects the endpoints, and the green tangent at point C has exactly the same slope, they're parallel. Key exam tips. First, f prime equals 0 is necessary but not sufficient for maxima or minima, you must verify. Second, the second derivative test is usually faster, just plug in the critical point. Third, if f double prime is also 0, fall back to the first derivative test. Fourth, for rate of change problems, always identify the chain rule connection between variables. Fifth, tangent slope is f prime, normal slope is negative reciprocal. Sixth, inflection points are where f double prime changes sign. Seventh, mean value theorem needs both continuity and differentiability. Eighth, for optimization problems, always check boundary values too, not just critical points. If you found this helpful, like and subscribe for more JEE and board exam solutions at MacPyHub.